My name is Matthew Shetrone. I am the Deputy Director for the University of California Observatories and a PhD astronomer. And my headquarters is at the University of California, Santa Cruz. And so I am currently observing from my home office up in the mountains above the campus. And so the chaos you see behind me is my home office chaos. But we are observing tonight on the Keck 1 telescope. And the way tonight will run is my co-partner on this project, Charlie Sakari. I'll introduce here in a moment, and she will give us an introduction to the science because she's sort of the intellectual lead for this project. And I'm just the guy who got the telescope time. So and the way this will work is we're splitting the night since our target is Andromeda, and we can't really use the first half of the night to observe Andromeda because it's too low. And so we're only using half the night. So there is somebody currently using our instrument. So I don't want to show the instrument too much because I might accidentally move something I'm not supposed to move. So we're going to talk about the science a little bit with Charlie for about 45 minutes, and then we will show you the transition between one observer and the other, and I will try to narrate, and there will be another Zoom session running that we're working with also that allows me to talk to them. So if you see occasional interruptions, that's what that's about. And so with that, I'll introduce Charlie, Dr. Charlie Sakari, and she can talk about where she is and some of the science.
Yeah, so hi everyone. Good to see you. Do you want to do the chat blast, Matt? Just have them say where they're from.
Right, sorry. I was thinking I could wait a little bit
Oh, yeah.
for more people to join, so maybe we'll do that
Okay, yeah, we can do
near
that
the
later.
end.
Sure. But yeah, I just want to say if you have any questions, you can put them in the chat or you can raise your hand in Zoom. I'm very familiar with online teaching, so I can manage those things all at once. And so, yeah, just feel free to jump in with any questions. So, I am a professor at San Francisco State University, an assistant professor, and I'm based in San Francisco, so not too far away from Santa Cruz. And yes, I'm going to tell you a little bit about the science behind this program that we are running tonight. So basically, the goal of a lot of our astronomy is to really understand the universe, right? Which is not a small task, right? We want to understand a lot of things, but one of the things we want to know is really what happened in the early stages of the universe, how the universe evolved, how it got to where we are now, and ultimately what are the physics underlying the universe. And so there's a lot of different ways we can get at this question, right? We could try and look at look back in time and see the earliest phases of the universe, or we can use a technique called galactic archaeology. And so galactic archaeology is, similar to archaeology on Earth, where they dig up old artifacts and use them in their old state to understand the behavior and patterns of civilizations from the past. And so we are doing the same thing here, but we are doing this with stars, with old stars. And so this is the Andromeda Galaxy. And so we can actually look at stars in the Andromeda Galaxy and we can ask questions like where and when did these stars form? How did they get to where they are now? How is this galaxy like other galaxies? And ultimately, are the properties of this galaxy consistent with the physics that we think underlies the universe? And so this is again just using these old stars as a way of understanding the behavior from the past. And we think we understand a lot about the universe and how things form and evolve. And our basic idea is that the universe is made of dark energy, dark matter, normal matter. You may have heard of these different things. Um, We think that galaxies assemble from mergers of these smaller dark matter halos. So this is a image from a simulation showing this process and how that works. And if we're looking at a galaxy like Andromeda or like the Milky Way, we can use observations of the stars and the star clusters that we see to really get at probing whether this framework that we have for the universe is correct. And so when we're looking at something like the Milky Way, we can ask, when do these types of mergers happen? What kinds of galaxies are merging together to form a galaxy like the Milky Way? And is the Milky Way an unusual type of galaxy, or is it more like a typical one? And so when we're looking at a galaxy um, and trying to assess, how did these mergers happen and those sorts of questions, one way that we can identify stars or clusters that have merged into the galaxy is by looking at stellar streams. So this is an example of an artist's impression of the Milky Way, and you can see, the beautiful spiral galaxy here. Let me get actually the fake laser pointer. So we see their beautiful galaxy here. And then this is a dwarf galaxy that's orbiting around the larger galaxy. And as it orbits around, it's shredded and forms these streams that wrap around the galaxy like this. And so if we're in the Milky Way looking out, we can actually see stars in these nice streams. And this tells us that they may have come from dwarf galaxies that are currently merging into the larger galaxy. Um, and so that's basically a lot of the idea behind this idea of galactic archaeology, is that we're going to use these old stars and understand a lot about this merging process. Now, one of the things about these streams is that they don't last forever. Eventually, they'll sort of dissolve into the larger halo of the galaxy, and we won't be able to see them after billions and billions of years. However, those stars still remember where they formed, and in particular, they'll retain the chemical signatures for where they formed. And this is important because stars actually retain the chemical signatures of their birth. So this is an image of a nebula. And so stars form out of the clouds of dust and gas in nebulas like this. And so they retain that composition of the nebula that they came from. And the composition of a star actually depends on the generations of stars that came before it. So if we see a star that's formed in this nebula, its composition is based on the stars that came before it and enriched that nebula. And so to understand why this is, we can look at an image like this, which shows really briefly the stellar evolution phases of stars. And so we start out here in a star-forming nebula where the stars form out of the dust and gas. And then we have two different cycles for a star, one depending on if it's a star like the sun and the other if it's a massive star. So if we have a star like the sun, it goes through most of its life where it's fusing hydrogen into helium in its core. Eventually it evolves and becomes a red giant. And then it continues to evolve and becomes what's called a planetary nebula, which has nothing to do with planets, but was named after how it looked. And then during that planetary nebula phase, the star blows off its outer layers and leaves behind a white dwarf. And for our purposes, we're interested in these winds that come off here and are blown off because those go back into the star-forming nebula or a different star-forming nebula, and new stars form out of that material. On the other side, we have these massive stars, and they evolve more quickly than stars like the sun. They go through a slightly different cycle where they become red supergiants or blue supergiants. They eventually go supernova, which also blows a lot of material off, and they may then become a neutron star or a black hole. But again, the material that's produced in the supernova or during the massive star phase also goes back into a star-forming nebula, and new stars form out of that material. So with this ongoing cycle, we see that stars are continually making new materials out of which new stars form. And so that's what we mean when we say that the composition of a star depends on the generations that came before it, because the stars we see here are going to have the chemical signatures of the stars that came before. And what's really cool for our purposes is that if we look at stars in different environments, stars in dwarf galaxies versus more massive galaxies, they actually have different chemical signatures. And so we're able to tell them apart based on their chemistry. So we're going to now take a little bit of a detour and talk about the periodic table, which is, it's 2:41 a.m. here, so this will be fun. Oh yes, Raja, you have a question.
Sorry, I just want to make ask a quick question,
Yeah, go for it.
clarification then. No, I love the way you explained this. And if we go back one slide, please, where you have
Yep.
the stream picture.
Oh,
So
yes.
I love the way you explain it. If we go back to the stream one,
Yes, just a
the
second.
animation. Oh, sure.
This one?
And sorry to disturb your
Yep.
narrative,
No
but
good. Yeah.
but I think you make you made the summary I'm hearing, and please correct me if I'm wrong, is once stars form, the chemical composition, at least of their surface, which is what we can measure, that pretty much doesn't get perturbed. There's talk of some pollution if a star swallows something. That's rare and sort of minimal in impact. So once a star is born, it's sort of locked in for billions of years if it's a low mass star. And you're studying low mass stars in Andromeda.
Yes.
I study low mass stars in Andromeda. So it gets locked in for billions of years, that chemistry that it came with. By contrast, the velocity of the star, they're all coherent, with other members that came off the same dwarf galaxy, but that coherence doesn't last for that long. It gets perturbed by other accretion events, substructure in the halo, any passage through the disk. So what you're saying is over time, both as a pattern on the sky, these streams, or kinematics, how stars are moving, that memory gets erased on the matter of, even less than a billion years sometimes. Whereas
the position, like the clumping of stars in the sky, that's the first thing that gets erased. Depending on where the stream is, the time scale will change, right? So if the stream goes very close to the center of the galaxy, there's a stronger gravitational influence from the stars there, and so the stream may maybe dissolve more quickly there, whereas over here it may last longer. And then
that's a great reason for studying the outer halo. The persistence of memory of the kinematics is longer, but chemistry doesn't care. It stays unpolluted for billions of years.
Yes, exactly.
Okay.
Yeah.
Great. Thank you. I just wanted to chime in with this.
Yep. And the kinematics are useful too. So that means how the stars are moving. Those still are useful to see how stars are moving together. Yeah.
They retain their coherence a little bit more than the spatial position, right?
Yes.
So that's once the stars are born, they hold on to that. But the gas that might be in that galaxy that's whooshing around, that may be influenced by the orbit. So one that is close in, maybe the gas is stripped out, or perhaps it does star formation at a different rate than the one that is further out. So the gas that's in the galaxy could be influenced, or in the galaxy that's orbiting could be influenced.
Yeah, and also to your point about the retaining the chemical signature, one other thing is that there are a few elements that do change a little bit as the stars are evolving, like carbon and nitrogen. But for the most part, they keep their chemical signature for their lifetime. Yeah. Yeah. Any other questions while we're stopped here?
And sorry for that very long interruption.
No problem. All right. So yeah, back to our periodic table. So this is what we call the astronomer's periodic table. You may have seen this before, where we have hydrogen, helium, and everything else is metals. And this is a historical thing why we would call these metals, because of course we don't normally think of them as metals. We'll talk about maybe a reason why this is useful in a moment. But we are interested in more than just this periodic table, right? We are interested in the elements that make up the periodic table. And so here is a version that has all the elements color-coded by the different astrophysical sites that could create these elements. So the different types of stars or evolved stars that create these elements. And so we'll break this down a lot more shortly and talk about what this means. But what I want you to take away from this at this point is that there's a lot of elements here and there's a lot of information that could be useful. And if you look at sort of like the top part versus the bottom part, you might also see there's a color change, right? We go from like a blue-green scale to a, orange-yellow scale. And so the blue-green is showing us exploding massive stars and exploding white dwarfs, whereas this bottom part is showing us, merging neutron stars and dying low-mass stars. So we're getting different types of progenitors in the different parts of the periodic table. So we ideally would want to be able to get measurements for as many elements as possible. So how do we get this information? Well, for stars, if we want to get this information, we will look at a star and then we will take the light from that star and spread it out into a spectrum. And so here this is shown with a prism. We will be using a much more complex instrument than a prism for this, as we'll see momentarily. But when you take the light from a star and you spread it out into a spectrum, if you do this at home with a prism, with the sun, you'll see something like this, a perfect rainbow. And maybe you can't see the purple end, but you'll be able to definitely see, blue, green, yellow, orange, red. If you use a high-tech instrument like the high-res instrument that we're going to be talking about tonight, you'll actually see something that's more like this. So we have that rainbow spectrum there, but on top of it, we have these dark bands, which we call absorption lines. And so these are areas of the spectrum where there is light missing. So light has been absorbed. And to understand why this happens, we can think about what our star is doing in space. And so here is a very, very not to scale cartoon of our telescope here. This is a huge telescope sitting on Earth and looking at a star. And if we imagine that our star is here, like kind of as a light bulb in space, just sitting there, we might expect, okay, the light is going to travel toward us and produce this perfect rainbow. But that's not what's happening. Instead, our star actually has an atmosphere to it. And this isn't an atmosphere we can breathe, right? Of course not. We'd, melt and die. But it's a thinner layer of atmosphere surrounding this star. And so when light comes out of the star, it, is being produced in the core through fusion, and it comes out through the star that's very opaque. Eventually, it can start to escape and go through the atmosphere. And as it goes through the atmosphere, it encounters these atoms that are present in the atmosphere of the star. And those atoms are able to absorb the light, but only at very specific wavelengths or colors of light. And so this is why we see these dark bands here, because this is due to the presence of these atoms that are absorbing very specific colors of light or energies of light. And so this means that we can look at a spectrum and we could see, for instance, this line here, and we could say, okay, that's hydrogen. And this line here, which is actually two lines, is sodium. And the way that we look at spectra is not like this rainbow spectrum, unfortunately. It's very pretty. You'll see them in looking different than this in black and white. But after we go through the process to take the images and process them, we look at spectra like this. And so this is a very, very small section of this of the solar spectrum, so of the sun. And what we see here is at 1 here, this is brightness versus wavelength or color. At 1 here would be this perfect rainbow spectrum. So 1 would be like we're just modeling this perfect rainbow. And so then everything that we see that's dipping down below 1 here is where we have darker features. And so these are the absorption lines. And so in this small region that I've plotted here, I've labeled them based on the elements that have created these lines. And so we have iron lines here. We have a vanadium line here, probably an element in the periodic table you've never heard of. We have barium and silicon and zirconium and sodium. So quite a lot of different elements just in this small wavelength region. And so we can use the presence of these lines to figure out what's present in the atmospheres of the stars. And we can use how strong they are, how deep, how much light they're removing to figure out how much of the element is present in the stars. That's what we would call the abundance of the elements. Oh,
And
Raja,
Charlie, I was just going to say that the Roman numeral 1 or Roman numeral 2 is
yes,
referring to ionization state. That's not iodine. It's not barium
yes,
iodide. It's or calcium
yes.
iodide.
Exactly. Yeah. Yeah. That's the ionization state. So it refers to how many electrons it has. And so unlike chemistry, we use a different term, we have a different terminology. So iron 1 means that it is neutral. So it has 26 protons, 26 electrons. So positive, negative, 26 of each, you end up with 0 charge. Barium 2 means that it's missing 1 electron. Yeah. Yes, so we can get a lot of different elements and abundances of these elements. And what's cool about these is that these elements have different nucleosynthetic sites. So that means they form in different types of stars and at different time scales. And so if we go back to this periodic table, we can see, an element like barium has very different nucleosynthetic sites than an element like iron. So something like the ratio of barium to iron or the ratio of europium to iron is going to give us information about the generations of stars that came before the ones that we're looking at. And so this is useful for understanding the timeline of the universe and what's going on and which stars have contributed to the chemical composition of the universe. And so if we go back to the timeline that I showed at the beginning, where we start with the Big Bang and then we proceed through the first stars, first galaxies until today, we're particularly interested in understanding the early universe. And so if we think about what's going on in the early universe, because if we look back at our periodic table, iron comes from exploding massive stars and exploding white dwarfs, we actually don't have any of those things before the first stars form. So that means in the early universe, we don't have any iron. There's no iron in the universe. All of it is coming from stars. Once the first stars form, those early massive stars can create iron, and then subsequent generations make more iron. And in general, in the universe, the amount of iron goes up over time. And so this is what we refer to as the metallicity of a star or a cluster. And so you may hear us use that terminology, but this is basically the amount of heavy elements, which we often use iron to characterize that. All right, so that's sort of a general outline of what we're doing with the spectra. So the other thing that we want to talk about is the type of targets that we're looking at. So we are looking at a type of object called a globular cluster. And so this is an image of a Milky Way globular cluster taken with the Hubble Space Telescope. And you see it's beautiful. Globular clusters are my favorite objects because they're so beautiful. And in the Milky Way, all of the sort of classical, typical globular clusters we see are old. That's not the case in other galaxies, but that's the case in the Milky Way. Most galaxies, all massive galaxies, have a large number of globular clusters. And so these are a good way to study the merger and assembly history of galaxies as well. So we can use stars, we can also use globular clusters because there's lots of them, they're plentiful. You may have heard of another type of star cluster, or hopefully seen it, called an open cluster. And so this is an image of the Pleiades open cluster. And you can see the difference between the two. A globular cluster is globby, and an open cluster is open. And so, yeah, a globular cluster has many, many more stars. An open cluster has fewer stars. You also see that, these are different scales on the sky, but you see that we have a lot of blue stars here, and that's because open clusters are very young. So these are young stars. And in the Milky Way, most of the globular clusters are sort of out here in the outer regions. And so this is showing, looking at the Milky Way from the side where we have the center of the galaxy here, a bulge that surrounds it, and then our disk where our sun lives. And the globular clusters are kind of scattered out here in the halo of the galaxy. And so this is an important point because as we were talking about before, when we look at our streams that we want to investigate, right, the globular clusters are going to sort of populate a lot of the outer halo. But another important fact is that simulations suggest that globular clusters form during periods of really intense star formation. And so they're going to be useful for understanding periods like the early universe when we had a lot of really active star formation. And there's a lot of open questions about how do globular clusters form. And so one interesting thing about globular clusters is that if all of the stars formed out of the same nebula at the same time, you would think they would all have the same chemical composition, but the stars do not in a globular cluster, which is an interesting thing. And so if you look at a cluster like this one, this is M15 or Messier 15, a Milky Way cluster. You can look at the individual stars in this cluster and you could see that actually all of the clusters in the Milky Way have some spreads in light elements like oxygen or sodium. And this particular one has a known spread in other elements like barium and europium. And so this was the subject of one of my master's students' theses, Jonathan Cabrera Garcia, and he looked at stars in this cluster M15 to characterize the spread of these elements. And so this is another useful thing we can do with looking at spectra of clusters is we can get an idea of the abundance spreads within them. And this is an important part of their formation. However globular clusters form, they have this spread in light elements and possibly spreads in other elements as well. All right, so let's go back to Andromeda. So we are going to be looking at globular clusters in the Andromeda Galaxy. And so here is a very nice image from an amateur astronomer looking at some of these globular clusters in M31. And as you see in this image, they don't look like the beautiful picture we saw with the Hubble Space Telescope. In this image, they actually just look like stars. And so to kind of understand why this is, here are two Hubble Space Telescope images of globular clusters. This is our friend M15 from the Milky Way, and this is one in the Andromeda Galaxy. So both taken with the Hubble Space Telescope. And I've put in here, these are not on the same scale. So they're not the same physical size on the sky. If I were to make them about the same scale, it would be something like this. Approximating with the limits of PowerPoint here. But the idea is that the Andromeda globular cluster is much further away than the one in the Milky Way. And because of that, it's physically smaller on the sky, just because it's further away. Now, this presents a real challenge for us, because if we want to look at stars in these clusters, we have to think about how to do this in a way that's going to be effective. So in the Milky Way, we can see these individual stars very clearly. And so we can take a spectrograph slit or fiber, and we'll talk a little bit about what that means in a moment, and put it on a star in this cluster and get a beautiful spectrum of an individual star. But for this cluster that's so far away, we can't do that as easily. And so we're going to actually put that slit or fiber on the entire cluster. And this is a technique that's called integrated light spectroscopy. This was a lot of the work of my PhD work back in the 2010s. And this is much more complicated than working with a single star, because now you have an entire stellar population that's there. And this makes things a little more complicated to analyze. But that's the gist of what we're doing with these clusters. All right, so that is the science part that I have. Are there any questions about what we'll be doing? All right, I realize I also forgot to put up the pandas, the pandas image. So let me pull that up really quick to explain why we're looking at these clusters. And you can tell that it's the middle of the night because I'm very slow and typing incorrectly. Don't just Google pandas images, because you will get images of pandas, like exactly what you think. But instead, I'm instead referring to a survey. And so let me just pull up this image here. We can look in the browser. I mean, you can just Google images of pandas. That sounds fun too. So this is an image of the Andromeda Galaxy. And this is from a survey called the Pan-Andromeda Archaeological Survey, or PANDAS. And what we see, oh, I see. Yeah, we have a chat. Yeah. Oh, yes, I'll answer that in just a moment. Yeah. And so what we see is they have kindly put an image of M31 here. So this is our visible light image that we're used to seeing. And this PANDAS survey is observing much further away from that. So it's observing these outer regions of the Andromeda Galaxy, and in fact covering this neighboring galaxy as well, M33. And so this was a really groundbreaking survey because it revealed in the outer regions of M31 all these wonderful stellar streams, like we saw in the illustration of the Milky Way with its streams. So we have, this giant feature here that's aptly called the giant stellar stream. And we have, this eastern cloud and the southwestern cloud. We're very creative with our naming in astronomy, our northern stream. But all of these features in the outer halo here are the remnants of dwarf galaxies that are being shredded. And another important thing is that these streams have on top of them globular clusters. So let me bring up that image for you. So the dwarf galaxies that are being accreted are bringing in with them globular clusters. And this means that we can look at these globular clusters and use them to understand the dwarf galaxies that are being accreted. So yeah, here is a black and white image of the outer regions of the Andromeda Galaxy, and then on top in color are globular clusters that have been discovered in the outer halo. And so, here's one of the streams, the southwest cloud. And on top of this stream, we see 1, 2, 3 globular clusters and another suspected one down here. And so it looks like this dwarf galaxy that created this stream brought in at least these 4 clusters, although there's some evidence that maybe it actually wraps around the galaxy. And this stream up here, the northern stream, this one has, 1, 2, 3, 4, 5, 6 possible globular clusters. And for this program, we have observed two of these clusters. And then over here, which one are we observing first, Matthew?
We're observing PA4.
PA4.
Which is,
I think it's one of these. Yeah.
Yeah, PA4 is in the northwest stream.
The northern stream. Yeah, it's one of these. Yeah, perfect timing. Yeah. And I think another one that's possibly associated with this stream over here. So yeah, there is a large one. Is M32 in the large stream. So M32 is sort of more in the inner region here. Yeah, I think there's some people who think it might be associated, but most people don't think it's associated with that large stream. Yeah. And then there was another question, is integrated spectroscopy a commonly used technique? So yes and no. So yes, people have used integrated light spectroscopy for a very long time, since like the 70s or 80s. But what's a bit unusual is we're going to do this at very high spectral resolution. And so we're going to be able to resolve, individual spectral lines as best we can. And that's relatively uncommon still. There's only a few people doing that kind of work. Yeah.
And I just want to say that the giant stream does go close to M32 as projected on the sky, but we are measuring velocities, and we can see that the stream has a velocity of minus 700 at the location of M32, whereas M32's velocity is minus 180. So they have more than a 500 kilometer per second difference. So the M32 can't be part of the current wrap of the stream. It may have wrapped around and at a different velocity. It may be I'm not saying there's no physical association, but not with the current orbital phase of the giant stellar stream.
Great, thanks.
Yeah. So any more questions?
I did note that the globular clusters along the streams have similar colors, and that's great news. That means they have similar velocities and suggests an association.
Yeah, here they're color coded by their velocities, and these are corrected to M31, so they're relative to the galaxy. And so yeah, the similar colors means that they're moving in similar ways. Yeah, and this is important because when you get like over here, there's a lot going on here, right? So it's not just clear that, oh, because there's a cluster that just lies along this stream, it's not clear whether it belongs here or whether it belongs to this one or, this blob up here, or whether it's just coincidence. Because, yeah, we're looking at a 2D projection of a 3D object. And so it's possible that, these clusters could be in front of these streams. And so, yeah, how they're moving is very important here. Yeah.
That's awesome. So we are about 10 minutes or so away from the handover for the instrument high res. And so I thought I would show you a little schematic. If I can do that. Oh, that's the wrong page though. So this is the schematic. So HiRes is a somewhat complicated instrument, and there's lots of light bounces and things that go on in the description. But the light comes into the instrument over here, and the very first thing it comes across is an isolating plate. We call that the slit. And so that means that you're not taking a spectrum of everything you see, but only kind of one area. And so on the sky, this looks like a black square. And that's because we have a guider image over here that this plate is reflective. So it reflects everything that doesn't go into the instrument. And so in the image, you'll see later, you'll see a black square, kind of like what Charlie showed of the globular cluster with this black square on top of it. So, and then the rest of the light goes into the instrument and goes to collimating mirrors, and then a grating, which separates the light into its spectrum, and then more mirrors and lenses. until finally it comes down to a camera. So so the light is actually separated out. Instead of just a long rainbow with red on one end and blue on the other, it's actually separated out into little tiny chunks so that the format of the rainbow fits very well onto the spectrograph. So it's red in one square, and then or one line it's the ultraviolet, and then the not quite so ultraviolet, and then the blue, and then the green, and kind of keeps going and going until you get up to the top where you're looking at the reddest colors that we can look at. So it's sort of a rainbow that's been sliced and diced and then reformatted onto a square format for the detector.
And Matt, I guess the first of the Echelle gratings, the first of the gratings is the Echelle grating that has the rulings along one direction, and then the cross disperser has the rulings in orthogonal direction. So it actually turns the spectrum into what looks like sentences in a paragraph. Right? You read across, and then you read down and across, just like sentences in a book. I mean, whether you're reading up or reading down, that's sort of.
That's a great way to put it. Thank you. Let's see. So there is a chat. Let's see. What did that say? Oh, okay. All right. Then let's check on the weather here. So tonight, the seeing here is a plot that shows the seeing individual measurements with two different types of measuring the seeing. Seeing is very good. It's typically less than 0.6 arc seconds. So that's outside the dome. So that does not include the dome environment. But that means we're probably going to get very good night. And then here is an image of the sky. This is a sky camera that's located at the Subaru telescope. Let me reload it. This was loaded a few hours ago. Log file. There we go. Copied, and then we're good to go. Okay. I don't know why it changes colors there right at that moment, but oh, that was a car driving by. So somebody's car headlights changed the scaling. But you can sort of see here's the Keck 1 telescope, and there's the Keck 2 telescope. This telescope is kind of zooming all over the sky, observing different objects. When we do our observing, it will be locked in place, pointed at Andromeda, so it will not be moving around anymore. You can see the Milky Way, you can see Jupiter, and that's about the extent of my knowledge of the amateur open sky. But there are no clouds that you can see. There's a little bit of stuff moving through that's either high-level atmospheric OH lines or a little bit of water vapor. Some glow on the horizon. So last night there was kind of a strong glow from Kilauea over here. And tonight the volcano is a little bit quiet. So I don't see a strong glow from Kilauea. The glows over here on the horizon, I think this is let's see, maybe Kona here and Waimea and Waikoloa Village, these other glows on the horizon. So you can sort of see there's just a hint of humans impacting only the nearest horizon. So that glow does not extend up into the night sky very far. Okay, stop sharing. Yeah, so it looks like a great night for us. And let me check to see if, yeah, so I checked, and our telescope operator and perhaps our support astronomer may be joining us a little later. And so that will be Heather and Greg may be joining in, and they may introduce themselves. But what I haven't heard or anything from our people who are here, I'd like to hear what country or state you're in. So if you can put into the chat kind of where you're from, that would be kind of fun to see where people are. Roger, where are you currently?
I just put it into the chat. I'm at home in Los Altos, California, but I'm traveling in a couple of days to the East Coast. So,
wow, it's dedicated. If you're on the West Coast, that's a pretty tough time to be awake.
oh wow, Charlie, you went to UVic. I had no idea. I was on sabbatical at HIA for a year.
Oh,
and I
yeah.
spent a lot of time at UVic as well at that time.
Yeah, British Columbia is a beautiful place, as Rebecca knows. Yeah. Yeah. Oh, South
Wow.
Africa. Yeah.
All right. You get the award for being the most displaced from either where we're observing from or from where I'm observing from.
So Annalisa has been a regular on Shadow the Scientist. This must be, and so has Rob. I've actually met Rob in person in LA, and Annalisa, we've only met on Zoom, but Annalisa has been a regular.
Okay, I'm gonna let's see. So Greg, are you going to join? Did you get the email with the Shadow the Scientist link? Okay.
I was saying I would jump on as soon as we do the switch here.
Okay.
Which we're just about to do. I think, in fact, Nick is reading out his last file now.
All right. So what we're going to do is.
Can I do the system stop here on the exposure limit? Yes, I do.
So you may hear some other conversations going on in the background. That's the support astronomer is going to help us transition from what they were working on before to the new instrument. And let me share the desktop. So this is what my desktop looks like with all the different stuff that I'm doing. And he's extremely efficient. And he's moving around up here on the upper left. The different components, the cross disperser, the shell grading. He's doing it so fast that I can hardly narrate fast enough to. Okay, and I guess I should pick out our first target. Heather, can you? Oh. Heather, can you join in the or have the other list, the observing list?
Yeah, you can map your star list whenever you want.
Well, I don't see the list in the.
You can map this. You have to go to File, Map Away Star List.
Right, but.
And then you go to wherever the OA Star List tab was, and it should have PA4 at the start.
Correct. Oh, there it is. I see.
All right, I'm Rob. I'm gonna go ahead and log out. Okay, thanks. See you next time. See you next time. Thanks for. Thank you. Okay, let's see. Right.
So the near horizontal white stripes you see in the lower left panel, those are the different shell orders. Those are the sentences in a paragraph I was talking about. And in this case, shortest wavelengths are at the bottom, longest wavelengths are at the top, as I recall, for high res. In fact, I can see the telluric emission lines at the top. So you sort of read from left to right, and then you step up one, read from left to right again, and that's how you count up in wavelength. So the shell grating has this peculiar property that it will take the white light from an object Sorry, Matt, I hope I'm not.
No. Thank you for being.
So the Echelle grating, it takes white light, and not only does it sort of stretch it out into the different colors of the rainbow, it does so for different wavelength regions, but it would all land on the same part of the silicon device if it weren't for the cross disperser. The cross disperser then takes the different orders and separates them vertically from one another. So you need both to make sense of the spectrum. One creates all the sentences, but would print them all on top of one another on the page. The other one separates the sentences vertically. I shouldn't say sentences, lines of text.
And just a bit of trivia, the word échelle in French means ladder. And so it's like climbing up the ladder of the different lines of text.
Ready to go here? Let's turn this iodine cell off. So let's go and iodine cell. We want to shut down the iodine cell.
And it's currently in. We want it out, right?
Yes, that's right. So you want to make sure it's out as well. Iodine menu. Oh, we do that over here on this control. So that's heaters off. We want to take it off.
Great, thank you.
Bye. Yeah. Okay, I think we're all set, Matthew. We've got your radiance angles. Your Decker 3 is in. Filters are set. The shell and cross disperser angles are good. And the directory's changed. You're in 2x2 binning. To the test exposure, it reads these out. So I think we're all set. We can also dismiss these guys. And all right, I'm gonna give it over to you, and I'm gonna jump on the let me on it. Put a head register.
Oh, that's interesting. So we.
That's right. The way it's set up is everyone has to register to get a unique Zoom link.
Okay, yeah. So I just informed that what I gave to you was not satisfactory for you.
They can use it. They'll show up as Matthew Shetrone. That's the only thing.
Well, since it wouldn't let them join. So
it should let them join. They'll just show up. It'll show up with your name.
Yeah, it did not let them.
Didn't let them.
They had to register.
Oh, gotcha.
I think you can't have two Matthew Shetrones.
I guess not.
Gotcha.
Yeah, there can only be one.
There is only one, yes.
All right, my apologies. So we'll have to, yeah, that'd be great.
Yeah, that's okay, good. I need just for that to hang out.
So can you hear the other Zoom session? Okay.
Yes.
I can hear it over your speakers a little bit.
Okay.
So I guess I need to leave. So I need to leave this Zoom meeting. It looks like it's prompting me to leave and join the new meeting. So I'm going to do that now. Unless I should stay on this call. But I think the link that you sent is working for me. So I'm going to launch the new meeting here. Okay, now it's letting me put in a passcode. Okay. Somebody fix this.
Matthew, you have a twin now. So we did this without realizing this. We did this once. There were 97 Brian Lemons on the call all of a sudden.
So in this upper right image, you can sort of see there are multiple slits here, different slits that could be selected for high res. The one we're going to be using is the middle one. And so if Heather can hear me, we're going to want to save an image before we actually get the object onto the slit so that we can document what this thing looked like before we put it on the slit. And then I'll save some images when we are on the slit. So Greg, are you on? It's hard for me to see who's on.
Yep, I'm on. Hi, everybody. Can you hear me?
Introduce yourself and say what
Great.
your job is.
Yeah, sure. So I'm a staff astronomer here at Keck Observatory. So my job is to enable observers like Matthew Shetrone here to get as efficiently as possible get their data and making sure that that the equipment that they're using, every aspect of obtaining the data is going as well as it can. So we're basically a facilitator of the science in that way. And of course, any troubles with the instrument, we're the first line of defense is to find out what the problem is and try to fix it ourselves. Or if we can't, then we go down a list of names to call and help with the problem. But fortunately, everything seems to be going quite well tonight, and the conditions are fairly excellent so far, knock on wood.
And so, Heather, are you on?
Heather may need the passcode specifically if she's connecting from a Polycom.
Looks like I got logged out of the other Zoom as well.
And Greg, I think you should be able to go into Zoom and change your name to your real name.
Oh, okay. Oh, I see. It's got, I'm right there is my real name. And
okay, so
let's see. Oh, I guess my video is back on now. There we go. So the picture behind me is of a storm that we had on Mauna Kea a couple of winters ago. So because even though we're in Hawaii, you can still get a fair bit of snow up there sometimes because it's almost 14,000 feet.
So I'm not in communication with Heather on either location. So Greg, I may need you
I see.
to.
I can take a photo here. Oh, see. So I see. You wanted to get a picture.
Well, yeah, and I want the object moved over a little bit. Aha. Hello, Heather. Okay, can you move over to the right a little bit? I want to be at the 1/3 point instead of right in the center.
Okay, so you want me 1/3 away from
the edge. Okay, just a couple of offsets to the right, as it were, and then.
Oh, and one other thing we want to set up.
And we want the rotator mode on.
Rotator position angle mode.
Rotator mode?
For the high res, so that it tracks the field, so that it does
PA position angle.
PA mode, yes.
PA mode.
What position angle do you want it at?
This one's fine.
It's gonna change to something else because it's gonna go to. Okay, hang on a second.
Is that because there's a second object in the slit?
No, it's just because we won't be able to guide on the slit.
Gotcha.
That's a gigantic slit, so it makes it very difficult to guide on the object. So we guide on something else in the field.
Where's this rotating to?
I don't know where it's rotating to.
How wide is the slit that you're using? And it's 11 arc seconds in length, right?
This is D3, and D3 is 7 by 2, almost 1.7. 7 by 11.1.7.
Wow. This is to capture as much light as possible from the globular.
Correct. Yes.
Let's see, we want, let's set this up for you, get your log going.
Well, better you can get this.
So the reason we're using the rotator is that normally when people use high res, their objects are fairly bright, and so they can guide directly on the slit, on the image that's reflected off of the plate that isolates the object. But with our giant slit, we have to observe or guide on something else, and the whole field rotates because of the configuration of the telescope on the sky as we sit there for an hour. And so if you're locking one point over here and the field isn't rotating with it, then the object will wander off. And so we have to compensate. Sorry, let's see. Yes, that looks good. No, that looks great. And once you're guiding, I will start the observation.
Okay, there you go.
Okay. And at the end of this object, if I don't forget, I'd like to push the object off of the slit for a moment and take an image so that I have kind of documenting what it looks like. Is that clear, Heather? Did I?
Yes.
Okay.
Okay.
Okay. All right, so so almost all of the object is falling within this slit. It's a very little globular cluster. Some of the others peek out the top and the bottom, but here you can just barely see any. Okay, so sorry, Heather, that you could not join.
Yeah, I'm wondering if it's because my Zoom is connected to my personal email and this is messing us up somehow.
But
it also says I need to register, so.
I think everyone can hear you. If you wouldn't mind introducing yourself and say what your background is, then that would.
Sure. I'm Heather. I'm a telescope operator. I've been here for about 17 and a half years. And my background actually, I got a master's in astronomy. And then I came out here and decided I really like telescopes, so that's where I am.
Thanks. So one thing that I like to emphasize is that it takes a little marching army to make observatories work. And so there are technicians, there are engineers, there are people in the business office, and those business office people are important because they let us get paid. So it takes a kind of a small army. And so all of those people are helping us do astronomy.
That's very true. There's a lot behind the scenes that allow us to be in this position right now, collecting data with the telescope, and all the systems are running. The mirror is, actively controlled to be the shape it needs to be to bring light to a focus. Sending it through, into the instrument here and having it disperse the light correctly. All of that needs to be working, which it is. Okay, so we're going to copy your FITS files over here. I'm just getting ready to display your slit image that you just took. Iris slit, yeah. So let's do that.
Just realized I'd set it for 1 hour exposure, and I meant to do 45 minutes, so I've just changed the exposure
Yeah,
time.
you can down select it with no problem. All right, let's get your slit image displayed. This is the one you just took.
Oh, I will share what you're doing here. Let's see.
Okay, let me flip the about. I see we flip about X. Is that right?
Y.
Yeah. Okay. Oh, Y.
Okay.
Flip about Y, not X. Zoom for Y. There we go. Okay, let me zoom out a bit here. Okay. Oh, I see this. So that's the.
So everyone can see you type.
All right, let's see. So let me just make sure we have. So the frames that you took, I just have this one that you took. You took another frame where the object was out of the slit. Is that right?
I did not.
Okay, so we can get that at some point.
Yeah, Heather was moving too fast. I couldn't keep up. So we'll do that at the end of the observation. We'll take one with it. But you can sort of see, well, it's a little hard to see. It's almost star-like in its size.
Yeah, so you can see two parts of it on either side of the slit that are just barely visible. Otherwise, most of the light, 95% of it probably is getting through the slit here. That's why we don't see it. And that's the light that's going into the spectrograph, which is where the science is coming from.
So the science we do is a little bit, thankfully, boring while we're actually doing it. So it's not frenetic. We take long exposures. So this one will be on for 45 minutes, and this will be the last of several 45-minute exposures we've taken over many nights. And then we'll move on to another globular cluster, and we'll probably stay on that for at least an hour. And then we will finish off 2 other globular clusters. I've kind of spread them out over several nights to get various conditions and to make sure I at least get a little bit of data on each one, so I know which ones are good ones or bad ones. And Charlie and I have 5 nights in a row. And so this is night 4. And so I'm a little bit bleary-eyed from observing and lack of sleep. Okay, let's see. Stop my share so I can.
We can, yeah, there's always the weather stuff too. If you're curious on the browser here on Tel Status, we have some.
Yeah, I'll go back.
Things we could show there if you want to.
Sure.
Share that one.
Yeah, I did share the seeing, so that's
okay.
Pretty good seeing.
There's this all sky camera it's got this fisheye lens of the whole sky. You can see the beautiful image of the Milky Way.
That's from yesterday, so you can sort of see.
Oh, that is from yesterday, so it hasn't actually.
Well, don't refresh it yet. You can see Kilauea in the lower left, the red glow on the horizon, and then you can sort of see it get bright in the east on the left side as we hit twilight yesterday. So go ahead and hit the reload button, and we will see what it looks like now. That glow is not there. So Kilauea, she's very inconsistent. Sometimes she's erupting and sometimes she's not.
Yeah, the glow is not as pronounced as last night. Anyone know what these bright objects are? Hint, one of them is a planet.
Jupiter and or Saturn.
I believe you're right.
Yeah,
I didn't realize the other one was Jupiter. The bright one, I think, is
Jupiter.
Jupiter, yeah, and Saturn must be right behind it. See, Saturn just it reached opposition recently, so maybe it's ahead of Jupiter now. Anyway, both of those are distinctively bright.
Okay. Let's see.
So where the cameras? Yeah, this is a view also taken it's not of course right now, but this is a view of a camera we have mounted on the top of one of the dome, the Keck 2 dome. If I refresh this page, you're going to see nothing because it's really a dark night out there. I guess I can do that just to show you.
Glorious dark night.
Yeah. If I just pan around a little bit,
Yeah, this globular cluster that we're observing, let's see, PA4 is its total magnitude. That whole cluster is 17th magnitude. So if you think about how faint that is compared to what you can see in your amateur scopes, it's pretty faint. I did have a friend when I had back in Texas who has a very large amateur scope, and he and I spent one evening looking at all of these globular clusters in Andromeda, trying to see if we could tell if they were star-like or whether they were a little bit soft, a little bit fuzzy, like bigger than just a star in Andromeda. We could just make out that they were not point sources. They weren't like a star. They were bigger than a star. But it sure was hard to see the faintest ones.
This view on the browser is the light path going into the instrument, the spectrograph. And you can see there's quite a bit of activity going on, a lot of things happening here with how the light is treated once it reaches the slit. Most of it gets through the slit, so it continues on through in this dotted blue line. And then there's a set of filters here that allow us to separate out unwanted light before it would hit the detector. And then after that, it reaches some optics that take the light and turn it into a collimated beam, so parallel wavefronts. And so that then it's able to interact with the gratings. The first thing it sees is the shell grating. The second is the cross disperser grating, which takes the light and basically splits it up into its wavelength colors. And then the light gets refocused by these optics down here and then imaged onto the detector here, which you'll see reading out here in about another 1950 seconds.
Hey, let's see.
This spectrograph delivers very high spectral resolution, and so as a result, it's very useful for radial velocity studies. In fact, the team that came on for the first half was using it for that specific purpose, to characterize the motions of exoplanet host stars. And with that information, you can get a complete, along with imaging that's been done before you can get enough information to basically map out the orbit. the orbital parameters of the exoplanet going around this host star. And it's remarkable to think we can measure the speed of something that's moving in space that's at about the scale of a person running. About 15 meters a second or so.
I have an image handy of Pandas 4 if the to see the size, if that would be helpful.
Yeah, fun.
Yeah, okay. Yeah, so this, let me move the zoom window. This is the catalog of these clusters from the Pandas survey. And so these are, you know, each of these is a little snapshot of the cluster. And this one here, this is Pandas 4. So you can see it's pretty concentrated here as compared to something like this, right? Much more spread out. Yeah, Pandas 6 is a little bigger.
The one we may do next is, and we have not observed this one yet, 22. I'm curious what it's going to look like.
Yeah, it's this one.
It has.
No, these are all globular clusters that belong to Andromeda Galaxy, right next door to us.
They may not all be globular clusters. There's some that look like there may be open clusters, like 24 maybe.
Yeah, so these are the extended clusters, they're called. Yeah. Yeah, some of these are I mean, we're only seeing the red giants here, so you know, we're not seeing the main sequence stars, so they're probably more stars than a typical open cluster.
And 41, that's one that we observed
yeah,
the
this
other
is
day.
the one that, yeah, it's missing half of it because it was right on the edge of the detector in this. And there's this, you know, galaxy looking thing here.
Mm-hmm. I think Greg saw that one and was like, "Ooh, is that a galaxy?"
Yeah. It's exciting to see, you know, okay, that's definitely not a point source. So then you realize you're looking at something that's outside of our own Milky Way galaxy.
We're looking at another galaxy through another galaxy. So this is a galaxy that's further than Andromeda. So we're looking through Andromeda at another galaxy. So it's kind of mind-bending to think about.
Yeah. Yeah, and 52 is another one we've observed. Yeah, these really nice, big, bright, obvious ones, those are the ones we observed years ago because they were the easier ones to observe, like Pandas 53 and 54. And some of these have Pandas 9 here has this really bright star next to it. So this kind of ruined this photometry. But we took a spectrum of this one last year, and we just, you know, had the spectrum, the slit not on that bright star there.
And actually, Charlie, I've got an image of the spectra from our proposal. Let's see if I can bring that up. So this is a set of very strong spectral feature due to magnesium, these three strong lines here, and some iron lines and calcium lines on the side. And PA37 is this deepest black line, and so we call that metal rich. The lines are quite strong from it, while the one she just pointed at, PA9, is the green one. And so you can sort of see there's noise in the spectrum, but the lines are very, very much weaker. And there's also some information there about the width, which can tell you something about its rotation. The one we're on, PA4, we thought maybe we're done with, but we decided that the noise level we could improve on understanding a little better if we is the blue one. And so we have some data on it already, and we just wanted to add just a little bit better signal on it. So that's the one we're observing. So these are the way you can make kind of a comparison, one spectrum to another, understand the differences in them. Okay. Have about 25 minutes before we change targets. Any questions for us? They don't have to be related to the work we're doing here.
Hi, Raja. Just want to say.
Oh, Heather's here. Great. That's nice. Thank you.
How are you, Heather? It's good to see you.
Yeah, I'm doing all right. It's been a while since we've had you observing.
I'm going to be out at Keck in October, and we'll be doing a bunch of Shadow the Scientist. So I have 3 nights in October.
You're gonna, and Halloween maybe?
No, pre-Halloween.
No, I'm working
be
that
there from
night.
the 5th to the 10th.
Okay. Yeah, I'll have to look. I think I'm off that week, sadly, but.
So Heather, how many nights in a row do you work?
Well, that can depend on when people get sick and all, but typically about 5 to 6.
And then how many nights off do you have before you come back on?
Well, since those 5 to 6 can be up to 15 hours each, I have about a week off.
So that means you're almost half your life is spent working on the telescope at night.
Mm-hmm. That's how it's been for about that time.
My previous job, before I took this job about 3 years ago, was in a similar role. I was a service observer at a Q scheduled telescope in Texas, the Hobby Everly telescope. And I was in shifts of 3, so I did a third of my life at night. And so over the course of 22 years, that's a lot of nights. And my wife was thrilled when I stopped working nights and she could spend more time with me. And she thought, that it wasn't going to wreck my health anymore. That's right. Science never sleeps. And if you're a radio astronomer, it's even worse because you can observe during the day, you can observe during the night. So I would not enjoy being a radio astronomer.
One of the telescopes on Mauna Kea, the IRTF, they are often open in the daytime observing a planet because that telescope points exceptionally well. So they can basically find targets despite the incredible sky background that you would otherwise be fighting to try to see anything. But in the infrared, these things are quite visible. So you can get to them and take spectra of them even during the daytime.
And IRTF stands for infrared.
So that's NASA's Infrared Telescope Facility.
And
that's
so
right.
The sky is very blue, and so it's not very bright in the infrared because it's blue.
That's right. And that's a reason why for infrared observations, they tend to get scheduled in a time of the month when the moon could be full. And so it would otherwise bother optical astronomers like us tonight to be observing during a full moon. In the infrared, they don't care.
I guess it's 2 effects, right? It's the spectrum of the sun, which most of the light comes out in the optical, not infrared, but also the properties of dust in our atmosphere tend to scatter blue light back at us, not so much red light, and even less infrared light. So,
yeah, unfortunately, the seeing is often not all that great during the day compared to the night because the atmosphere is more turbulent. So even though the infrared is better for day night, there is a big difference between the seeing. The atmospheric turbulence still gets some solar heating, and so the turbulence is more pronounced. Okay.
I have a quick science question for Charlie and Matthew. You're no doubt familiar with Janet Colucci and Rebecca Bernstein's work on integrated spectra of global clusters with HiRISE, I guess, most of it.
Yes.
And I guess these are different because they're tracing streams?
Yeah, these are clusters they didn't look at. Yeah, and Janet Colucci has left astronomy, so she's not doing this work anymore.
Yeah,
Rebecca was sort of the groundbreaking scientist for this effort in high resolution mode.
Right. Judy Cohen was part of that effort, I believe. Also, Judy, Rebecca, and Janet were doing this. I was on Janet's thesis committee.
And Andy McWilliam as well.
Andy as well. That's right. And they were doing some work with the Southern telescopes as well. I think the Magellan, I think with Mike,
yes.
possibly.
Yeah.
No, this is wonderful. It's great that you're doing this. I've been a friend of Andromeda's for a very long time. I remain a friend of Andromeda's even now. So.
Matt, I just noticed that Pandas 22 is, oh yeah, never mind. Maybe it's okay. They're all listed magnitude is 0, but I guess that's.
Yeah, I think that's just a quirk.
Yeah,
that would be so nice.
Typical for
yeah.
Yeah, it's as bright as Vega.
That would be pretty cool, but also
we'd really be able
not.
to.
That's why astronomers typically use 99 as a magnitude flag.
Yeah.
So I think it was the Greeks that are responsible for the magnitude system being set up as the way it is.
They were so smart, right? They were so smart. They knew there were things that were fainter than the eye could see on most nights. So they were so smart about that. And Charlie, just a complete change of topic, but one of my former students has joined you guys at SFSU. This is Charity Way.
Oh, yes, right.
It's super excited to be in your grad program. And
yeah, I've heard of Charity. I think I know what she looks like. I interacted with all the grad students when they came. I had a lunch with them. Yeah. She'll probably be in my class next semester, my observing class.
And she's been working a fair bit with demo spectra and trying to understand the ins and outs of different reduction pipelines. So
I had an event up at Lick Observatory as a appreciation night for the volunteers that help us over the summer. And I was sitting down with a woman who's a volunteer and asking them what their interest was, what their connection to the observatory was. And she said she works at UCSC and is interested in going to graduate school. And she was thinking she needs to kind of stay in the Bay Area for family reasons. She was looking at San Francisco State, and I said, what kind of work you're interested in? And she said, well, there's this younger faculty that's very exciting that's doing exciting work that I might want to work with. And I was like, oh, who's that? Charlie Sakari. It's like, oh, well,
it's a small world in the Bay Area. Yeah.
Was it the same student? Was it Charity? No.
I can't remember. It could be. No, she hadn't applied yet, so I don't think it is.
Yeah, if you just were up there, it Yeah.
Yeah. Yeah, she was going to apply this year. Everybody wants to work with Charlie.
Which is a blessing and a curse.
Yeah, including me. I want to work with Charlie.
Yeah, we have 2 new faculty actually, which is really nice because now we have more people to take on students.
That's in addition to Adrian, Joe, and yourself?
Yeah, and John Brewer was hired at the same time as me. He works on exoplanets and exoplanet hosts using the Express spectrograph. And we just hired Eileen Gonzalez, who works on brown dwarfs and giant exoplanets, and Oscar Macias, who works on the Galactic Center and you know galactic centers in general, and particle astrophysics, that sort of stuff, high energy.
Wonderful.
Hey, we're counting down 15 minutes before we change objects. I thought it might be kind of nice for everyone to see us change objects one more time before we call it a night. So we have a little time to kill.
I guess we could explain what's in the different windows and stuff.
Sure. Let's see. See if I can find Control-0 easy here. Here we go. Greg probably can say better than I can. So this is we use this desktop for control of the instrument. So we have a thing that allows us to control the end of the night calibrations. So I can type in here, like, we're going to take 20 bias frames, and we're going to take 20 flat frames and 2 thorium argon frames, and with different filters. And there's 2 different quartz lamps we can choose, and 2 different thorium argon line lamps. So the lines produce emission from the elements thorium and argon, and that creates a spectrum that is just filled with known emission lines, and we can use that to help calibrate the instrument as what the wavelengths are in each of the lines of the book of the spectrum. And so at the end of the night, I'll hit go, and it will take a whole bunch of exposures. This is the instrument control. So earlier, we were showing this, and you probably saw Greg very quickly moving through and changing. The iodine cell was in. They were using that to help search for planets. It creates a picket fence of absorption features that they can use to very highly calibrate the velocities of the object they're observing. The filters that he mentioned in the configuration, which shell grading and which slit we're using, the shell angle, the cross disperser angle, so how that's configured. And then here we can control the CCD and set the exposure time. And you can sort of see how much time has elapsed, and we're counting down the exposure. We have a progress bar at the bottom. Anything else we should say about this frame before we move to the next one?
I think you've covered it. Mostly there's even more information in the instrument control down at the bottom here. There's information about the Dewar levels, the liquid nitrogen that we use to keep the CCD detector down at minus 130 centigrade requires us to keep liquid nitrogen in the Dewar continuously. And so this monitors the levels of the nitrogen and it will automatically fill itself up from a storage dewar, which is the reserve dewar here listed at 86%. The main dewar, when it gets to 10%, will autofill from that storage dewar and keep itself from running out. And then there's even more information about the electronics and the coolant and the temperatures, all these things we want to. It's nice to have a quick view that everything is okay. We don't have any trouble with temperatures getting too warm in the electronics rack, for example, which would be a bad thing.
So you notice the mouse moving around. This is one of the really cool features that that the pandemic has really made useful in innovating, is that I have the same view that Charlie has, that Greg has. And so I can move the mouse around, or Greg can move the mouse around, or Charlie can move the mouse around, and we're all seeing the same desktop. And so I don't have to be physically there on the mountain. Greg, I don't know if you are doing this from home or you're in the office.
I am currently at home.
Okay.
So yeah, all of the staff astronomers have access to the support that we need to do from home if needed. And that's in fact what we had to do during pandemic. I think we were down for maybe 4 weeks in between March and April of 2020 while we scrambled to get this observing mode set up. We call it pajama mode, where you can observe from your bedroom, like many of us ended up doing in the pandemic, to maintain the support that we needed to keep the observatory running. It really changed the whole game. So now it's so convenient for anyone to jump on and observe or just shadow. It's a great tool for, it's not just convenient for us, but also a great learning tool for anyone who wants to see how the observing is actually going up close and intimate here.
Yeah, that's okay. All right, so there were a couple of things here in the chat. Did that get all sorted out?
Yes. Yeah.
Okay. All right. Let's try another desktop. Let's see. Control. Okay. So how about that one? So this is the next one in the list. So this is a displayer there are 3 detectors, and they are stitched together in this particular view. There's the blue at the bottom, sort of the green, and then the red at the top. And before, when we first started, you could see the last image of the last observer of his planet, or of the star that hosts planets. And you could see the features of moving from left to, or the spectrum from left to right. They were in little lines, like lines in a book. This is a bias frame that we use to test to make sure that it looks okay when we changed configurations that Greg took. So we don't see anything there yet, but we will in another 474 seconds. Anything else we should mention in that screen? Mostly that's what that's for. Okay, and then let's see if I can find number 3 to share. And this is mostly telescope control. And so in this GUI here, we have the image that is off the reflective surface at the beginning of the instrument. And so the light that goes into the spectrograph is in this black slit. It's all the light that goes into the spectrograph, and then everything bounces off to a camera, everything else. And so if I zoom out this way, can sort of see the other stars in the field, and Heather has selected that particular star to guide on. So there's a box that is drawn around that object, and then the software looks and says, oh, it's drifting a little to the left, it moves it to the right. So the object stays on the slit. I tend to stay zoomed in so that I can sort of see, drawn a little circle to remind me where I should be looking, that the object is not quite centered on the slit, it's off to one side. And I can sort of see if it starts to drift one way or the other. And then over on the right, you see kind of a summary of where we're pointed, the current local sidereal time, so the coordinates of the sky that are directly above us, the universal time. That's not the University of Tennessee time or the University of Texas time. That's universal time. It's at Greenwich Mean Time. And then a lot of other information about the telescope and some weather information below. So Greg or Heather could probably say more about those.
The plots below show so there's some really useful at a glance telemetry of the current weather conditions on the summit. These in this plot on the left, you have various temperature plots. So you have the temperature of the secondary mirror in the sort of the pink color. The green is the primary mirror's temperature. That's at about 4.4 centigrade. And then the dome temperature inside the dome is 6. It's a little warmer actually in the dome than the primary and secondary mirror at the moment. It's tracking more of the temperature outside, which is the cyan color. So this basically shows you all these temperatures and what they're trending, are they staying flat? We want them to stay flat, but sometimes they'll be changing as conditions are changing. Then there's plots here to the right of that. You have the humidity plots. So you have the outside humidity is the light blue, and then the red is the humidity inside the dome, which should be roughly the same since the dome is open to the outside air. So we see there's been a general trend, increasing trend of humidity, but nothing to be worried about. We're still below 40%, but it's a little higher than usual right now, I would say. I'm sure Heather has a lot more stories about weather and that sort of thing, having been a telescope operator for 17 years, you said? I've been a support astronomer for 12.
17 and a half.
So you're over the 2-decade mark. Excuse me. Well then,
not quite yet, but getting there.
Yeah.
And Heather, where are you observing? Where are you controlling the telescope from?
Well, tonight I'm actually at headquarters. Usually we're up on the summit in the control room, but we've been testing out some modes for working from headquarters, which, was very helpful in the past. I had a time where I couldn't go to the summit because of an illness, and being able to work down here was very handy. So that's kind of partly. It also allows people to rush in at the last minute if someone gets sick on the summit. If we have enough people up there, someone could jump in here and hold the fort until things get settled out. It's okay being down here. I didn't get to see a nice sunset, so I was a little sad. The trees over here block it, sadly.
Do you find it easier to work there at headquarters?
It's a bit of a wash in some ways to me right now because I'm not by the telescope, so I have to call other people, I have to look through cameras, I have to figure some things out. So my usual mode is kind of off. I guess I don't feel quite as tired right now as I probably would if I was up there on my first full night. So, but and I'm more hydrated down here for sure. I mean, I see the humidity's gone up a little bit, but you don't really notice that very well in the control room. So it's nice. I mean, I get to decide what I want for dinner in a different way down here. So we basically have a sort of a cafeteria up at this base camp we stay at called Halipahaku, which means House of Stone. or stone houses. And basically there was, they make meals for us. So, because we're really far away from town when we're on the summit, we can't just pop in and get a burger or something. It's whatever they make that night is what we're getting. So tonight I got to decide, sort of, depending on what was open in Waimea, which is the other side issue.
Village Burger.
They were closed.
Oh my God.
I showed up 5 minutes too late. I thought they closed at 6, but they closed at 5, and I was like, no.
They're the best burger on the island.
Yeah, they were really good. They put a fried egg on it, which when I was at UVA, there was a place nearby that used to do that, and I was like, oh, they do it. It's so good. But no, it was my plan tonight, but I showed up 5 minutes too late, so I had to go. I had to figure out something else. I'll have to try them another night.
So Heather, in 1 minute, this exposure will be over, and
Yep.
if you will move the object off the slit just enough so that I can save an image.
Just vertically, fine.
That's fine. Yeah.
Okay. Yeah, I'll pop it up about 5 or 10 arc seconds.
That'd be great. And then once I confirm that I've got those images, then we can move off to PA22.
The final countdown.
Yeah.
Exciting. All those photons have been getting collected for the last 3/4 of an hour.
And if you hadn't been here, I might be sleeping, and then all of a sudden I would hear exposure complete to wake me up.
Now you start to see the as the detector reads out here, you'll see the different orders.
Below the slit, you probably noticed there. Do you need me to change the exposure time for you or anything?
How long is your exposure?
3 seconds at the moment for guiding on another
10
star.
seconds? That would be great.
10 seconds? Gotcha.
Yes, please.
All right, let me wait for the long 10-second readout.
And in this image, you can just see that it's a little bit fuzzier than the stars above it. Let's see.
The next image should be full 10 seconds.
Okay.
There we go.
There we go. Save fits image. Okay, ready to go.
All righty.
Now you have a nice image of the spectrum.
Oh, yes.
In control 1. Yeah, if you want to share that, that's...
Let's see. Maybe I'll share the whole desktop so you can sort of see stuff's happening all over the place. Yeah, so in the lower left, you can sort of see the spectrum of and so the slit is sort of arranged vertically, and so these
you want
lines.
me to pop it off before I put it on there?
Yes, please.
All right. Yeah, I'll do it another 10 seconds here. Hang on. All right. You can take an image.
I'm saving an image. Great. Could you put it on?
I see those images. I see those images that you took, and I will display one of them right now in the DS9 on tell status.
Okay. Look at us. Everybody's doing something different on another screen.
Another beauty of the Zoom phenomenon. Well, I guess Zoom doesn't have anything to do with it, but we can all be talking to each other while also accessing the same screens, any and all of the screens together or separately.
What is that bright emission line in the middle of the high-res frame? Is that 5577?
let's see. So that's in the
green.
Green, right?
chip,
5577.
it's sort of the, yeah. So I think you're right.
Okay. Looks like we're positioned again.
Okay.
Still on that right side a little.
So I should be changing this. We are observing PA 22.
Yep. Make sure all your files line up with the FITS headers.
1 hour. Oops, why didn't it update? Come on. PA 22 for 1 hour. Okay. Great. So yes, I think that you're right, Raja, that I think that's this feature you were talking about.
Yeah, so it looks like a doublet there, bright doublet. Or maybe it's a single line.
I think this might be sodium. But all of these others up here are probably OH, the molecule oxygen and hydrogen together. And they glow. This is what, the 5577, that's O2, is that right? And then this is sodium 1, or neutral sodium.
I think 5577 is O1, but I'm going to look this up.
O1, oh, you're right. I'm sorry, O1. I think you're right. And then the other thing that is very obvious here is all of these specks, the speckles all over the spectrum. And these are all due to cosmic rays. Yeah, so there's one that is kind of coming in at a steep angle. And so these are charged particles. Some of them are from outer space, and some of them are from sources like radioactivity in the rocks. And they hit the detector at funny angles and knock off electrons inside the silicon. Since we're exposing for an hour, there's lots of them. So we have to take multiple exposures to be able to say, filter them out somehow. I remember at another observatory, tried very desperately to reduce the number of cosmic rays that were getting to the instrument. And so we had lead bricks that we built kind of all around the instrument, only to discover that the lead was full of things that had decayed to lead, like thorium and uranium. And so we were actually getting more cosmic rays from the lead bricks than we do from the cosmic sources. So we had a lot of spare lead bricks to put someplace. Hey, I'm gonna stop sharing. Oh, yeah, stop sharing. I think that ends pretty much everything that we wanted to share with you. You saw us change targets. You know, the science we're doing. Hope you had an enjoyable evening.
Yes, thank you so much.
Nice to have you along. Keep us company, keep us from falling asleep.
And Matthew and Charlie, thank you for hosting. This was your first time as STS hosts, and thank you for doing this. And it really, thanks to you guys, this is the first night when we've had two different hosts again on the same night. Our hope is to have so many people host that we can do this more often. Thank you.
Thank you, Raja, for putting it together. This is, I was just saying, you know, this is really an important part, kind of a dying trend in astronomy is people that observe and take their own data at the telescope and know how to make real-time decisions about adapting to conditions if they're changing. These choices are important to know how to make. And as you know, more and more observatories are Q scheduled, people don't, these skills are becoming lost. So
one
thanks
of the
for
things
participating.
I was just going to say, one of the things that Gemini North is doing is they're actually shadowing on Q scheduled nights, and that's being done by the staff, and it's really wonderful to see. It's you know, the other thing that's a dying art is critical thinking itself in society, and so when it's such a good thing for young people to see that there are adults who use critical thinking in their work. And
essential.
I think it has benefits well beyond science and astronomy.
Yeah.
Oh, thank you all.
Strong need. Thank you.
Good night, all.
Good night.
Thank you. Have a good evening.
Bye.
Too.
Thank you, everyone.
Bye. Bye.
Jamika, should I do an end for all, or is there something you need to do at the end here? Should I give hosting back to you?
Oh, no, not at all. You can go ahead and end it, Matthew.
Okay.
Let's stop the recording first, maybe.
Oh.
Yeah, we've been being recorded the whole time.
It will